Hi, I'm Dominic, and I want to show you today that one can get some vision-language correspondences without any paired data. Given different objects in the real world, both images and text are abstractions of the same underlying world. Using a pre-trained text encoder and image encoder, these abstractions can be mapped to two embedding spaces. The Platonic representation hypothesis mainly evaluates how close the distances between two objects represented in vision and the distances between the same objects represented in language are. So whether the cat is closer to the dog than to the airplane in both spaces. They find that with increasing compute and data, the pairwise similarities become more aligned. This means that for large enough models, the cat is probably closer to the dog than to the airplane in both the image and the text embedding space. Given a set of vision and language embeddings, we aim to identify which language embedding corresponds to which vision embedding. For this, we search the permutation of the text embeddings such that the distances in the language space align as best as possible with the distances in the vision space. We formulate this as a quadratic assignment problem. Unfortunately, current local solvers like optimal transport are often not enough to get meaningful correspondences. We introduced an heuristic called factorized Hahn-Grant, leads to better pairings in practice. Given our solver, our work shows that it could indeed be feasible to find matches between vision and language without any paired data, just using the pairwise distances in each space. Note that our work doesn't assume a shared embedding space, but only compares the distances computed in each individual space. This means that we can find correspondences also for completely unrelated vision and language models. Let's dive into the optimization problem that we need to solve. We are given a vision distance matrix between pairs of vision embeddings, and the same also for the language embeddings. We optimize over a permutation matrix that is 1 if the ith vision embedding is mapped to the jth language embedding, and 0 else. This matrix tells us in the end which vision embedding corresponds to which language embedding. Altogether, the objective is a quadratic function of the permutation matrices, called a quadratic assignment problem. So how well can vision and language embeddings be matched in practice? First, we evaluate on Cypher 10 and Cynic 10, which is basically Cypher 10 but with image and images. For each class, we compute a representative language embedding and a representative vision embedding. So this is a problem where we try to match 10 image representations to the corresponding language representations. Here we show the results for two different language models. We observe that most models can be matched with non-trivial accuracy. Especially the DynoV2 embeddings can be matched with high accuracy and therefore embed pairwise similarities very similar to the language models. For the All-Roberta large model in the DynoV2 on Cynic 10, we can recover all 10 pairings just using these pairwise distances. So does this work for arbitrary text and image embeddings? For this, we take ImageNet 100 and Cypher 100. On the right-hand side of both plots, we can see that for the whole dataset, the matching accuracy is only marginally better than random. However, this is only one part of the story. When we iteratively leave out classes that are not well aligned, we observe that many classes, like up to 20 to 40 classes depending on the dataset and the model, can be matched with high accuracy. So there are some classes that have very similar distances in both spaces. However, the steep drop shows that once you include certain classes, the whole matching is disrupted. So the distances are also very different for some other classes. Furthermore, as may be expected, supervised models perform better than self-supervised models, especially on very fine-grained classes. So the main takeaway message is that unsupervised matching can be formulated as a quadratic assignment problem, and vision embeddings and language embeddings can already be matched without any supervision. And this is made possible by similarities in the pairwise distances in both spaces. You can find more information on our solver, the experiments, and how to use matching to power unsupervised classification in our paper. Thank you for your attention.